Okay, so we're going to look at problem 1342. I'm going to do a recording of this, so if you wanted to go back and reference it, you're welcome to do so. Now, this is from Module 4, and in this problem, we're going to be looking at, it's going to be using the potential energy or conservation of energy law. So we have a roller coaster, and we have the car that we have some individuals in. It's starting out at point A here. And it's going to go down, it's going to go around the loop-to-loop and then over the hill, if you would, at E. So it says here that it's starting at rest at A, rolls down the track to point B, which is at the bottom of that loop-to-loop. Then we've got that circular loop. It's a 40-foot diameter or 20-foot radius. And then it's going to come up to, once it goes all the way around, up to point E, which then has this radius phi. Knowing that H is 60 feet and assuming no energy loss due to friction, determine the force exerted on the seat on the 160-pound rider at B and at D. Okay, so that's the first part. The second part is, what is the minimum value of the radius at E if the roller coaster is not to leave the track at that point? Okay, so we'll start with A first, obviously. So what we're going to do is I'm going to kind of put in our elements or the things that we know and what we're trying to find, and then we'll kind of go from there. Okay, so zoom here. I know for this problem, so this is application problem 1342. Okay. I know that my height is equal to 60 feet. The weight of the, just trying to see here, I forget. The weight of the rider in the car is 160 pounds. The radius of that loop is 20 feet, which is going to be equal to our rho C, and this is the radius of the loop-to-loop, which they have the center called C. Okay. And then we have gravity. So we'll be applying gravity. We know that to be 32.2 feet per second squared. I don't know, I put it on here. And then we want to find, okay, part A, we want to find the normal force at B. This is going to be the normal force, the support force, if you would, of the person in the car, and the normal force at D. And then part B, we want to know what that radius of curvature at point E is minimum. Okay. So what we're going to do is we're going to start this by looking at this at a couple different points. So the first point that we're going to look at it at, we're going to start at point A and we're going to go down to point B. Okay, so A to B is what we're going to be identifying. But we're going to look most specifically at what the riders are doing at point B. So if we look here, so this is going to be part of our part A, what we're trying to find here. But the first part is I'm going to look at point B. Okay. Now I'm going to identify going to the right and up is positive. And I'm going to just draw the cart as a block. And this is going to be the center of that block. We know that the weight is going to be going down. Okay. And we know that weight to be 160 pounds, right? And then we know at this point, the normal force is going to be pushing up. So this is when the car is at the bottom here. So, oopsie, it's at the bottom here. So its wheels are below it. So the people are on top and the wheels are below it. So the normal force is going to be opposing it. So the track is here, if you would. And this is the normal force at B. And we're going to set that equal to, okay, our center here. And we know that this is going to have mass times acceleration. Okay. So I'm going to put a line here and we're either going to put that down or up. Okay. So it's going to be the mass times acceleration. And I'm going to put the N for the normal. Now, why is it the normal component of acceleration? It is because this is the very start of going around a curve, okay? And the acceleration when we're going around a curve from the point is going to be towards the center of rotation, okay? So the normal acceleration then is going to push up towards that center of rotation when even though we're down here, it's going around that curve and its center of rotation is up here. So the acceleration is going to point towards that center of that center of rotation. So it's going to be going up. Okay. So now what we're going to do is we are going to say, okay, the summation of the forces in the y direction are going to be equal to mass times the normal acceleration. Okay. Now, as we look on the sum of the forces in the y, this is going to be a negative 160 pounds plus the normal force at B. It's going to be equal to the mass, which is going to be 160 pounds divided by 32.2. Okay. Times the acceleration normal. Now, from chapter 12, okay, I think it was chapter 12. The acceleration normal is going to be the velocity, the straight line velocity squared divided by the radius of curvature, and that's going to be at C. Okay. Now, this velocity can be calculated, and we looked at this in practice problem 1317 or sample problem 1317. So you can look back to that practice problem, but we know that the velocity squared is equal to 2gy, okay? 2gy. Now, that y distance is going to be the distance that the point that we're looking at, B, is from where we started. So we look here at A, the distance that we go down to get to B is going to be the full height. That's going to be 60. So in this case, y is equal to 60 feet. Okay, so we're going to use that value up here. So let's kind of, add a couple things here. We can solve for NB, because that's what we're trying to find for our problem. So I'm going to pull out NB. Okay, it's going to be equal to, I'm going to move my 160 to the other side, add it to the other side. So I'm going to end up having 160 divided by 32.2 times V squared. I'm gonna substitute the 2 times 32.2 times 60, okay? Because the y is 60, divided by the radius at C of that curvature, which is 20, okay? And then we're gonna say plus 160, kind of got, okay? So NB is equal to that. So now we know all of these values. So you should get MB equal to 1120 pounds. And NB is confirmed direction. So that means that it's going to be going up. So that's the normal force, or the force that is pushing on the person in that cart at point B. Okay. So do you have any questions on that, John? Does that make sense? The second part of this, yeah, that makes sense. Okay, so the second part of this, and I'm just going to kind of help you set it up. You're going to look then at point D. Okay. Now, point D, if we look on our roller coaster here, if our wheels are here at B, we're going to go around and our wheels are going to be up at D, but we're going to be upside down, right? And then, so when you set this up for point B, or I'm sorry, for point D, you're going to have the same block in each section, right? So you know that the weight is still going to go down, but this time our normal force is, if you would, our support is on the top here. So that means that our normal force at D is also going down. And again, it's just because of the orientation of where those wheels are. We're upside down now, if you would, or the people in the cart are upside down. Now, from the center, mass times acceleration normal, because we're at the top of that curve this time, the normal acceleration is going to point down towards the center of rotation. So that means that our mass times our normal acceleration is going to point down. Okay. So then you'll do that very same thing. Sum of the forces in the y equals m times normal acceleration. You're going to do that same substitution, but this time your y is different. Okay. Your y distance is going to be the distance from A down to D. So it's going to be 60 plus 40, or a negative 60 plus 40, if you would, or 60 minus 40. Okay. So that means that y is going to be 20, right? So make sure that you find your y distance relative to where you start, which was at A. And then you'll solve for, then you should get 160, it looks like, pounds down. Okay. And then trying to think what the last part was. Oh, the last part is going to be, then you're going to be at E. Your wheels are going to be down again. You're going to be sitting on top here. But this time, your phi is going to be what you solve for. Okay. And when it says here, if the roller coaster is not to leave the track, so that means that your normal force at E is going to be 0. It's going to be that point right when, you know, maybe that you're not leaving the track, but you're kind of feeling like you're not on it, if you would. Okay. So that would be the minimum radius that you would need then at that point. So you would set it up very same way, but then you're solving for the row there, that radius of the curvature. Is that helpful, John? I don't want to steal the opportunity for you to kind of go through the process. Okay. All right. Excellent. Well, then I will stop the recording here, and then I'll post it for anybody else who may find it handy. And yeah, let me know if you have any more questions.